Hello, we will now continue with our study of electric field by solving some simple problems. Let's start with example 1. A charge of 40 microcoulomb is at the origin. What is the magnitude and direction of the electric field on the x-axis at x equal to 6 meter and at x equal to negative 10 meter? Sketch the function ex as a function of x for positive and negative values of x. Well, the first part is very simple, is that right? We have a charge of 40 microcoulomb at the origin. We need to find the magnitude and direction of the electric field at 2 points, x equal to 6 meter and at x equal to negative 10 meter. Well, let's do a simple review. What is the expression for the electric field at a point, a distance r from a charge? Do you recall that equation? Well, we know that the electric field, if you have a charge q placed, what is the electric field at a point at a distance r from it? The electric field is a vector quantity given by E equal to kq over r squared. Now, if this charge q is a positive charge, the direction of the field will be directed away from it. Is that right? Because the direction of an electric field is the direction in which a positive charge would move. And therefore, if this charge is a negative charge, the direction of the field will be directed towards it. So, the magnitude of the electric field and the direction of the electric field. We should be familiar with both these in order to solve problems of this type. Alright, let's continue with our problem. Pick our data. What do we have? Since the field due to a positive charge is directed away from it, for positive x values, the field will be positive, and for negative x values, the field will be negative. Is that right? For positive x values, the field will be directed in the positive x direction. Because if the charge is at the origin, the field will be directed away from it. It means for positive x values, the field will be along the positive x-axis, and for negative x values, the field will be along the negative x-axis. Now here I have the x and y axis. This is the charge that is 40 microcoulomb. Now, what is the magnitude of the field at x equal to 6 meter? Where is x equal to 6? Let's say that is x equal to 6. What is the magnitude of the electric field at this point? Well, E equal to kq over r squared. And what is k equal to? 9 times 10 to the power of 9. Q is 40 microcoulomb. 40 times 10 to the power of negative 9. R equal to 6 meter. So using those values, we get E equal to 10 to the power 4 Newton per coulomb. And that's the electric field. Tell me, what is the direction of that electric field? What is the direction of the electric field at this point due to this charge? That's a positive charge. So this will be directed in the positive x direction. That is the direction of the electric field. Alright, let's go. And that its value is 10 to the power of 4 Newton per coulomb. Now, what is the magnitude of the field at x equal to negative 10 meter? Where is x equal to negative 10? Let's mark that. Will be E equal to kq over r squared. The only difference here is now r equal to 10 meters. Is that right? Alright. Now, use your values. That will be 9 times 10 to the 9 times 40 times 10 to the negative 6 over 100. That is 3.6 times 10 to the 3 Newton per coulomb. Now, if this is x equal to negative 10, then what will be the direction of that field? The direction of the field at this point will be directed away from the charge. So that will be the direction of the field, which is 3.6 times 10 to the 3 Newton per coulomb. So we found the electric field at x equal to 6 meter and the electric field at x equal to negative 10 meter. Now tell me, what do you think will be the shape of the graph if you draw a graph of x? Well, graph of electric field on the y-axis and of course x on the x-axis. You notice that for x values that are positive, the field when x is very small will be large and the field will decrease as x increases. Is that right? Yes. In the same way, for negative values of x, for very large negative values, the field will be close to 0, and as you come closer and closer to 0, the field will be a very large negative value. Is that right? Does it make sense? Yes? Alright, let's go and do that on the next slide. The function that describes the field intensity along the x-axis is Ex equal to kq over x squared. Now, k and q are constants there. The amount of electric charge is a constant. K is a constant. Therefore, what will be the graph like? The graph will be this. For positive values of x, the electric field will start out with a very large value, and as x increases, the electric field will decrease. For negative values of x, for very large negative values, the field will be close to 0, and as x gets closer and closer to 0, the electric field will increase, well, in the negative direction. Okay. The function only describes how the magnitude of E changes along the x-axis. Is that right? Well, actually, it gives you how the magnitude and direction changes, because on the negative side, this tells you the magnitude and direction. On the positive side, this gives you the magnitude and direction. Alright. So at points very close to the charge, the field is either positive or negative infinity. Is that right? When you come very close to the charge, that means when this x is very close to 0, the electric field will be either close to positive infinity or negative infinity. Alright, another problem. When a test charge Q0 equal to 2 nanocoulomb is placed at the origin, it experiences a force of 8 times 10 to the negative 4 Newton in the positive y direction. What is the electric field at the origin? What would be the force on a charge of negative 4 nanocoulomb placed at the origin? If this force is due to a charge on the y-axis at y equal to 3 centimeter, I think I'm going to change this as y equal to 3 meter. Alright? That will be more convenient. What is the value of the charge? Well, try and understand this problem and try and see if you can draw a picture of it. Once you are able to picture the problem, you can do it. So, what do we have here? When a test charge Q0 equal to 2 nanocoulomb is placed at the origin, it experiences a force. Obviously, if a charge is experiencing a force, it means that charge is placed in an electric field. So there is an electric field at the origin due to some charge. We don't know what that charge is. So this test charge experiences a force. How much? This is the amount of force it experiences. And what is the direction of that force? The direction of the force is the positive y direction. Well, tell me, if a positive charge is placed in an electric field, what is the direction of force it experiences? A positive charge experiences a force in the direction of the field. A negative charge will experience a force in the direction opposite to the field. Why? Because the direction of the electric field is defined as the direction in which a positive test charge will move. Therefore, a positive charge will always experience a force in the direction of the field, and a negative charge will experience a force opposite to the direction of the field. Alright, let's draw that picture. Here is the origin, and we place 2 nanocoulomb, a test charge of 2 nanocoulomb at the origin, and we are told it experiences a force of 8 times 10 to the negative 4 Newton. That's right. This is the force it experiences. Now, do you recall what is the relation between the force experienced by a charge and the electric field in which the charge is placed? The magnitude of the field, not field, could change that spelling. Magnitude of the field at the origin is E equal to F over Q0. Is that right? Electric field is force per unit charge. And therefore, the force experienced by the charge placed at the origin, F equal to E times Q0. Well, the electric field, we need to find the electric field, is that right? What is the electric field at the origin? The electric field is force per unit charge. Now, a charge of 2 nanocoulomb experiences a force of 8 times 10 to the negative 4. Therefore, the force per unit charge is 8 times 10 to the negative 4 Newton divided by 2 times 10 to the negative 9 coulomb. That is 4 times 10 to the 5 Newton per coulomb J. Now, what does that tell you? This force is in the positive y direction. The electric field is in the positive y direction. Now, how do I know if the electric field is in the positive y direction? Because I know that the force experienced by a positive charge will be in the direction of the electric field. Since the direction of the force is the positive y direction, the direction of the field also will be the positive y direction. Alright, so we did part A. B, what would be the force on a negative 4 nanocoulomb placed at the origin? Well, in place of the 2 nanocoulomb, if I place a negative 4 nanocoulomb, what will be the force on that? Well, force on a charge equal to electric field multiplied by the test charge. F equal to E times Q. Now, we know E, we know Q. Therefore, that will be 4 times 10 to the 5 multiplied by Q is negative 4 nanocoulomb. 4 times 10 to the negative 9. And that will be negative 1.6 times 10 to the negative 3 Newton J. How do you know that force is in the negative y direction? Because the force experienced by a negative charge will be in a direction opposite to the direction of the electric field. So that is the force experienced by a negative 4 nanocoulomb. How about C part? if this force is due to a charge on the y-axis at y equal to 3 meter, what is the value of the charge? Now, did you understand that? If this force, or it is the same as saying that this electric field, now remember, the force is produced by that electric field, 4 times 10 to the 5 Newton per coulomb. Now, what this part says is that this electric field at the origin is due to a charge placed at y equal to 3 meter. We were not told that earlier. You see, there is an electric field at the origin because there is a charge placed at the origin. What we need to now do is find the value of that charge. Alright, can you tell me, if an electric field directed that way is to be produced by a charge placed at y equal to 3, what must be the sign of the charge? Will it be a positive charge or a negative charge? I mean, yes, in order to produce an electric field in the positive y direction at the origin, due to a charge placed at y equal to 3, should that charge be a positive charge or a negative charge? I'm going to leave it for you. I want you to think about it. Alright, let's go and do the next part. We know that the force experienced by the charge placed at the origin is negative 1.6 times 10 to the negative 3 Newton, and this is the force experienced by that. Alright, if Q is the charge at y equal to 3 centimeter, I think I'm still carrying on with that centimeter, the field due to this at the origin, if this is the charge Q placed at y equal to 3 centimeter, then what is the field due to that at the origin? It will be KQ over R squared. That will be 4 times 10 to the 5 Newton per meter. In fact, that is the electric field we had in the beginning. We calculated that. And so, that Q will be ER squared over K. Is that right? Yes. Q equal to ER squared over K. We don't know what that charge is, but we know the electric field. We have calculated that electric field. 4 times 10 to the 5 Newton per coulomb. And that electric field is produced by this charge Q placed at y equal to 3 centimeter. Now, therefore we can now solve for that Q. Q equal to ER squared over K. And E equal to this, R equal to 0.03, well, that is 3 centimeter. So it is 3 centimeter, don't correct it. So let's put all those values. We know the value of E, we know the value of R, and we know the value of K. And that therefore is 4 times 10 to the negative 8 coulomb. Now, you've got to tell me, is this a positive charge or a negative charge? Well, how do you know? This charge has produced a field at the origin directed upward. That means directed towards the charge. So what type of a charge is that? That will be a negative charge. Only a negative charge will have the electric field directed towards it. A positive charge will have the electric field directed away from it. Alright. Let's do another one. 2 equal positive charges of magnitude Q1 equal to Q2 equal to 6 nanocoulomb are on the y-axis at y equal to plus 3 centimeter and at y equal to negative 3 centimeter. What is the magnitude and direction of the electric field at x equal to 4 centimeter? What is the force experienced by a charge Q0 equal to 2 nanocoulomb placed at x equal to 4 centimeter? Can you picture that problem? Well, I'm going to draw the diagram for you. There you are. A charge Q1 equal to 6 nanocoulomb is placed at y1 equal to 3 centimeter. A charge Q2 equal to 6 nanocoulomb is placed at y equal to negative 3 centimeter. What do we need to find? What is the magnitude and direction of the electric field at x equal to 4 centimeter? Alright, that means we need to find the electric field at x equal to 4 due to Q1, and also we need to find the electric field at that point due to Q2, and use the vector addition principle to add the two vectors. Alright, let's do that. Field at x equal to 4 centimeter due to charge Q1 is, what is the formula for field at a point distance r from a charge? Well, first of all, in order to find the field at this point, we need to know the distance of Q1 from that point, which is this green line. What is the length of that green line? You know that this distance is 3 centimeter and this distance is 4 centimeter, and therefore the length of that diagonal will be 5 centimeter. Is that right? Because 3 squared plus 4 squared equal to 5 squared. 3, 4, 5 are called Pythagorean triples. So the distance of Q1 from the point is 5 centimeter, which is 0.05 meter. So we have E1. E1 stands for the electric field at this point due to Q1 is KQ1 over R squared. We know all these values. 9 times 10 to the 9. Q1 is 6 times 10 to the negative 9 over R squared, 0.05 all squared. What is that equal to? That is 2.2 times 10 to the 4 Newton per coulomb. Alright, what is the direction of this field? Anybody tell me, what is the direction of E1? The electric field at this point due to the charge Q1. Q1 is a positive charge. The electric field due to a positive charge will be directed away from that charge. So the electric field due to Q1 at this point will be directed away from it. There you are. So this is the electric field, 2.2 times 10 to the 4 Newton per coulomb. Alright, let's now find E2, the field at x equal to 4 due to Q2. Now the distance of Q2 from the point is this same distance, 0.05 meter. Is that right? Okay, so E2 equal to KQ2 over R squared, and all these values are the same as before. That means the magnitude of this field vector will be the same. What would that be? 2.2 times 10 to the 4 Newton per coulomb. And what is the direction of this electric field? This also is a positive charge, means the field will be directed away from it. There you are. And that's your E2. Alright. Tell me, how will you add these two vectors? In order to add vectors, we first break them into their x and y components. And in order to do that, you need to know the angle the vector makes with the x-axis. Is there any easy way to find that angle? Anybody help me with that angle? Well, you should know that this angle is the same as the opposite angle, that is this angle. So, if this angle is theta, its opposite side is 3 centimeter, adjacent side is 4 centimeter, therefore tangent of that angle theta will be 3 over 4, and hence we can find that angle theta. If you know this angle, then I know the angle the vector makes with the x-axis. I hope that is clear. Alright, let's do that. Come over here, let's find the angle. The angle made by E2 with the x-axis is theta equal to tan inverse of 3 over 4. Remember, this angle is the same as this angle. Tangent of this angle is opposite side, that is 3, divided by adjacent side, that is 4. Therefore, theta equal to tan inverse of 3 over 4. And do that on your calculator. Tell me what that is. That's approximately 37 degrees. And the angle made by E1 then will be negative 37 degrees. That will be, the magnitude will be the same. So the angle made by E2 with the x-axis is 37 degrees. And the angle made by E1 with the x-axis will be negative 37 degrees. Can you now write E1 and E2 in terms of the x and y components? How would you do that? E2 equal to the magnitude of it, 2.2 times 10 to the 4 cos 37i, that is the x component, plus 2.2 times 10 to the 4 sine 37 degrees j. So 2.2 times 10 to the 4 cos 37 degrees is the x component of E2, and 2.2 times 10 to the 4 sine 37 is the y component. And use your calculator to obtain that value. That will be 1.76 times 10 to the 4i plus 1.3 times 10 to the 4j. So this is the x component, 1.76 times 10 to the 4. And this is the y component, 1.3 times 10 to the 4. You notice that I can draw the y component anywhere I want. I can draw it here or here. Alright, in the same way, can you write E1 as the sum of the x and y components? Yes. E1 equal to 2.2 times 10 to the 4 cos of negative 37 degrees I, that is the x component of E1, plus 2.2 times 10 to the 4 sine negative 37 degrees, that is the y component. And that is 1.76 times 10 to the 4i, that is this, there you are, minus, so this quantity is a negative quantity, minus 1.3 times 10 to the 4j, that is the y component. Now, you notice that the y components actually will cancel. The resultant vector will be the sum of these two. Tell me, what do you get when you add this vector to this vector? The y component of E2 is equal and opposite to the y component of E1. They will cancel. Equal and opposite, they will cancel. And the x components are the same and directed in the same direction, therefore they will add up. Alright, so the resultant field intensity E equal to E1 plus E2. Now when you add E1 and E2, the y components will cancel, the x components will add up. And that gives you, when you add these two, you get 3.52 times 10 to the 4i Newton per coulomb. And that is the resultant electric field at x equal to 4 centimeter due to these two charges. What is the next thing that we need to find? What is the force exerted on a third charge Q0 equal to 2 nanocoulomb when it is placed at x equal to 4 centimeter? So now you're going to place a charge Q0 equal to 2 nanocoulomb at this point. what will be the force it experiences due to this electric field. You are placing the charge Q0 in this electric field. What is the equation for the force experienced by a charge placed in an electric field? F equal to E times Q0. Is that right? Force on Q0 placed at x equal to 4 is F equal to Q0 times E. I hope by now these things are very clear in your mind, because E, the electric field, is defined as force per unit charge. And therefore, if a charge Q0 is placed in that field, the total force it experiences will be Q0 times E. Well, we know Q0, that is 2 nanocoulomb. We know E, that is 3.52 times 10 to the 4. And so that force will be 7 times 10 to the negative 5 Newton. This is a good type of problem. You must be familiar with doing these kind of problems. Let's do a quick check. A simple problem. Charge Q acts as a point charge to create an electric field. Its strength measured a distance 30 centimeters away is 40 Newton per coulomb. What is the electric field strength at a distance 90 centimeters from the charge? Alright? Can you visualize that problem? A charge Q produces an electric field of 40 Newton per coulomb at a distance of 30 centimeters. You need to find the electric field strength at a distance 90 centimeters from the same charge. Well, we haven't been given the quantity of charge. So what do? Alright, if E1 is the field at 30 centimeters away, then E1 equal to KQ over R squared. 30 centimeters is 0.3, is that right? Yes. So, we are told that the electric field at a distance 30 centimeters from the charge is 40 Newton per coulomb. And that is our E1. Let's leave it as E1. Later on, we will replace E1 by 40 Newton per coulomb. So E1 equal to KQ over 0.3 squared. Now, if E2 is the field at 90 centimeters away, can you tell me what will E2 be? E2 will be KQ divided by 0.9 squared. There you are. Now, we know the value of E1. We now need to find the value of E2, but we don't know the value of Q. How would you solve that problem? You have two equations, E1 equal to KQ divided by 0.3 squared, E2 equal to KQ divided by 0.9 squared. You need to find your E2. There are many ways to do that problem. Let me give you one method, the method that I have not used here. Use the first equation to figure out KQ. Look at this. KQ equal to E1 times 0.3 squared. Now, just replace this KQ by that, E1 times 0.3 squared. You can see, E1 we know, therefore we can find E2. But the method I have used here is, you can use this method in any situations of this type. What you need to do is divide equation 2. Divide this equation 2 with this equation 1. E2 divided by E1. Look at this. The left hand side, E2 divided by E1 equal to this quantity, KQ divided by 0.9 squared. Divide that by this quantity. Now remember, dividing by a fraction is the same as inverting and multiplying. So instead of dividing I multiplied by what? Multiplied by the inverse. So E2 divided by E1 equal to KQ divided by 0.9 squared times. Now you notice, where did that multiplication come from? It's supposed to be divide. Now dividing by a fraction is the same as multiplying by its reciprocal. So it will be KQ divided by 0.9 squared times the reciprocal of this is 0.3 squared divided by KQ. Now in doing so, KQ and KQ will cancel. So that gives me 0.3 squared over 0.9 squared. And we want to find E2. We know E1. So I can say E2 equal to E1 multiplied by this quantity. You can find the value of that quantity. The value of this quantity is 0.11. And therefore E2 equal to E1 multiplied by 0.11. And E1 we know is 40 Newton per coulomb. Therefore E2 equal to 0.11 times 40. That will be 4.4 Newton per coulomb. Now, it's a very nice way of doing problems like this. Alright? Alright, let's move on. Let's now talk about motion of electric charges in an electric field. When I started introducing the concept of electric field, I told you when a charge is placed in an electric field, that charge will experience a force. If a charge experiences a net force, that force should produce an acceleration. Alright, let's work it out one more time. Since a point charge placed in an electric field experiences a force, it will accelerate and hence move. Now, when a charge Q is placed in an electric field E, tell me, what is the force that it experiences? If a charge Q is placed in an electric field E, what is the magnitude of the force that charge will experience? Alright, did you get it? The force will be E times Q. Is that right? Or Q times E. The force experienced by a charge Q placed in an electric field E is F equal to Q times E. Now, the net force acting on any object of mass m is F equal to ma, where a is the acceleration that force creates on that charge. And therefore, I can solve this for A. If F equal to ma, A equal to F over m. Now, what is this force? The force experienced by an electric charge is Q times E. So, I'm going to replace this F by Q times E, and that gives me the acceleration of the object of mass m kilogram carrying a charge of Q coulombs placed in an electric field of E Newton per coulomb as A equal to, what I did is I replaced this F by QE. So acceleration is QE over m, or more conveniently I write it as Q over m E. I'm going to say that one more time. When a charge of Q that has a mass m is placed in an electric field E, it will experience a force, a net force, and hence accelerate. The acceleration of the charge is given by A equal to Q over m times E. Okay, make a note of these. A positive charge will experience a force in the direction of the electric field. We talked about that many times before. And a negative charge will experience a force opposite to the direction of the electric field. Very important to know that. The direction of the force experienced by a positive charge is in the direction of the electric field, and the direction of the force experienced by a negative charge is opposite to the direction of the field. Okay, let's do another problem. An electron has an initial velocity of 2 times 10 to the 6th meter per second in the x direction. So here's an electron moving in the x direction with a velocity of 2 times 10 to the 6th meter per second. Now, it enters a uniform electric field E equal to 400 Newton per Coulomb. So, an electron enters an electric field. An electron is a charged object. That means when it enters an electric field, it will experience a force. Now, what is the direction of the electric field? The electric field is directed upward, 400 Newton per Coulomb J in the positive y direction. Now, here comes an electron. Can you see the electron coming in? Here comes an electron, and when it comes to the origin, it falls in an electric field. The electric field is directed upward. Tell me, what is the direction of the force the electron is going to experience? Electron is a negative charge. So this electron is going to experience a force in a direction opposite to the electric field. The electric field is directed upward. That means this electron is going to experience a force downward. So an electron moving in the x direction suddenly experiences a force downward. That means it is going to move like a projectile downward. Is that right? Well, I hope you can picture that. Let's try and draw that over here. There you are. This is what happens. The electron is moving in the horizontal direction. And as it comes to the origin, it is now become, it comes under the influence of this electric field that is directed in the positive y direction. And therefore, it will experience a force opposite to the direction of the field. And therefore, the electron will move like this. In other words, it has a horizontal motion and a vertical motion. Alright. Find the acceleration of the electron. We can do that. By the way, what is the equation for the acceleration? Can you recall that? Acceleration equal to Q over m times E. And we have all those quantities. We know the charge carried by an electron. We know the mass of an electron. Well, you can get it from the tables. It's a standard quantity. Okay, the initial velocity of the electron is in the x direction. It has no initial y velocity. You see, when the electron reaches the origin, it has no y velocity. It has only x velocity. Therefore, I can say Vx0, that is, at the moment it is at the origin, its x velocity Vx0 is 2 times 10 to the power 6 meter per second. That is given to us. And Vy0, initial y velocity, is 0. Now tell me, from your understanding of projectile motion we did in part 1 of physics, what happens to this x velocity with time? As the electron keeps moving, what happens to the x velocity? Well, you must know that the x velocity will not change. Why not? Because there is no force in the horizontal direction. The force on the electron is only in the vertical direction. So the vertical force will not affect the horizontal motion. That means this velocity will not change. At the same time, the electron will start picking up a vertical velocity. Alright. Let's find the acceleration of the electron first. Since the field is in the positive y direction, the force experienced by the electron is in the negative y direction. And the acceleration in the y direction is, what is the acceleration? A equal to q over m times E. Q is the charge on an electron. How much is that? 1.602 times 10 to the negative 19. And m is the mass of an electron, and this is the mass of an electron. A standard quantity. It's nice to know that, but in problems like this, it will be given to you. Alright, so, and E equal to 400 Newton per Coulomb. So that will be 7.03 times 10 to the 13 meter per second squared. Which direction? In the negative y direction. So if I write it in the vector notation, this will be negative 7.03 times 10 to the 13 meter per second squared J. Well, I have only given you the magnitude, since you know it is in the negative y direction. So this acceleration is in the negative y direction, and I wrote it using the vector notation. A equal to negative 7.03 times 10 to the 13 meter per second squared J. Alright, now the question is, how long does it take the electron to travel 10 centimeter in the x direction? Can you do that by yourself? What is the x velocity of the electron? Vx, the x velocity is 2 times 10 to the 6th meter per second. Now, we just now said that x velocity will not change. That is going to remain a constant. Now, with this x velocity, the electron is going to travel a distance of x equal to 10 centimeter. Well, the velocity remains a constant, and with that constant velocity, the electron travels a distance x equal to 10 centimeter, which is 0.1 meter. Can you find the time taken to do that? Well, x equal to v times t, is that right? When the velocity is constant. Alright? That x will be equal to, this is the x velocity. We got x equal to the constant velocity multiplied by time, or the time is distance traveled divided by the uniform velocity. Well, the distance is given to us is 0.1 meter. The horizontal velocity we know is 2 times 10 to the 6th. Therefore, the time taken for the electron to travel that horizontal distance is 5 times 10 to the negative 8 seconds. Now, during that time, the electron is also falling. And therefore, we can now do the next part. Well, I wrote that time as 50 nanoseconds. What is the next part of the problem? Since the acceleration is in the y direction, the electron will deflect in the y direction. The question in the C part is, how far will the electron fall during that time? You see, during the time 50 nanosecond, we calculated the time. Time is 5 times 10 to the negative 8 meter per second squared. While it travels a horizontal distance of 10 centimeter, it is also falling at the same time. We need to find that fall of the electron. How much did the electron fall? Now, how do we do that? What is the initial y velocity? This time, we concentrate on the y direction. Alright? The initial y velocity is 0. So we will use the equation y equal to v by 0t plus 1/2 at squared. Can you recall those equations from physics 1? Well, our a, the acceleration we know, is negative 7.03 times 10 to the 13 meter per second squared. V by 0 is 0. Therefore, you can calculate the value of y. So that will be 0 plus 1/2 times a t squared, where t we calculated. And what does that give you? That will be negative 0.088 meter. So during that time, the electron fell through a vertical distance of 0.088 meter. Now, these are all good problems. I hope you got a fair idea how to solve problems using the concept of electric field. Well, let's do another problem. A mass of 2 grams located in a region of uniform electric field E equal to 300 Newton per Coulomb I carries a charge Q. The mass released from rest at x equal to 0 has a kinetic energy of 0.12 joules at x equal to 0.5 meter. Determine the charge Q. Well, we have an electric field E equal to 300 Newton per Coulomb, and we have a mass of 2 grams carrying a charge Q. The mass is released from rest at x equal to 0, and it acquires a kinetic energy of 0.12 joules at x equal to 0.5 meter. Alright, picture that problem. Now, let me try and draw that for you. Here is the origin. We have an electric field E equal to 300 Newton per Coulomb I. The electric field is in the x direction to 300 Newton per Coulomb, and you release an object at the origin, and we are told that in traveling a distance of x equal to 0.5 meter, it acquires a certain kinetic energy. It means it acquired a speed. That means the object is traveling in the direction of the electric field. When it came here, it has a certain speed because it has a kinetic energy. Now tell me, is this charge a positive charge or a negative charge? I will not tell you. If you don't know it, that means you have a lot of deficiency in this course. Alright? Okay, the charge is moving in the direction of the field, and only a positive charge will move in the direction of the field. Well, we can use the concept of kinetic energy to calculate the speed of the electron. Now, determine the charge Q. In order to determine the charge Q, we probably have to calculate the amount of force it experiences. Alright, let's go and start the problem. Okay, the mass is 2 times 10 to the negative 3 kilogram, and the kinetic energy is 0.12 joules. What is the kinetic energy of an object that moves with the velocity v? K equal to 1/2 mv squared. Now, you know K, you know m, therefore we can find v. V squared equal to 2k divided by m, and use the values of k and m, you get v squared equal to 120 meter per second squared. Well, let me ask you, the object that has a mass of 2 times 10 to the negative 3 kilogram starts at rest at the origin. Its velocity is 0 at the origin. And in traveling a distance of 0.5 meter, it acquired a velocity given by, this is v squared. V squared equal to 120 meter per second squared. Now, can you use this situation to find the acceleration of the object? What is the acceleration? If you recall some of the equations of motion, which of the equation you will use here? Well, you need to use the equation that contains the initial velocity, the final velocity, acceleration, and the displacement. Look at this. Vf squared equal to V0 squared plus 2ax. Well, we know Vf squared, that is 120. We know V0 is 0. We know x is 0.5 meter. Therefore, we can calculate the acceleration from this equation. You see how important it is to know these things. So from this equation, we're going to calculate our acceleration. All right, let's go and do that then. So we now find the acceleration using v squared equal to v0 squared plus 2ax. I'll replace v squared by 120 and replace x by 0.5, and that gives me a equal to 120 meter per second squared. Simple equation, because 2 times 0.5 is 1. A equal to 120 meter per second squared. Can you therefore calculate the force experienced by this charge? If acceleration is calculated and if you know the mass, can you calculate the force? Well, you know that acceleration is q over m times e. Well, we know the value of e, we know the value of m, we know the value of we know the value of A, therefore we can find Q. Q equal to A times M divided by E. And A, the acceleration we calculated, is 120 meter per second squared. Mass is 2 times 10 to the negative 3 kilogram. And E is 300 Newton per coulomb given to us. And therefore, that Q is 8 times 10 to the negative 4 coulomb, which is 800 nanocoulomb. I think we've used a wide spectrum of understanding of electric field to solve problems. And that is it.